quick video, or quick one. Bound particle to a sphere. We are building towards having a proton with an electron in the ground state and having a wave function that will represent that. So, first of all, I'm on pages 42 and 43 of my notes. I'm going to skip a lot of the mathematics because I don't have much time to actually write it all out. But I've step by step written out what you're going to, you can see how the equations build from each other. Okay, we are in 3 dimensions. However, when we're bound to a sphere, Cartesian coordinates are our enemy. What we want to do is convert to spherical coordinates. R is going to be constant throughout this whole thing. So from the center, I've got some R, and then I have 2 different angles, which since I have an extra angle now, that means I'm going to have an additional quantum number, which you'll see appear in just a little bit. So the colatitude angle, if you stand in a corner and you put your arm up straight into that corner, bring your arm down, that is the colatitude angle. And then until you move your hand away from yourself and smack the wall to either side of you, that's the azimuthal angle. So you can think about your head as the center of the sphere, away from the corner, that's colatitude, and then smack it against the wall or wherever you are with respect to the walls, that's the azimuthal. So that's spherical coordinates. Okay, so we now have our wave function, psi, r, theta, and phi. Let's take the Hamiltonian of that. And that's going to equal E psi of r, theta, and phi. But since r is constant, we're not going to take that into consideration. And so what we're going to be left with is a psi of just theta and phi. So now, because of separation of variables, just like we did before when we had psi of x, y, and z, we had f of x, f of y, or g of y, and h of z, we're going to have now big theta of theta and big phi of phi. So now we have 2 different functions multiplied together to give us our 2 angular components of the wave function. Now, these have also interesting properties, just like when we solved for the wave function for the harmonic oscillator. We had to take into consideration all the boundary conditions associated with the spring. Same thing. This is going to take into consideration the boundary conditions associated with that angle away from the corner of the wall or down this direction. And then this is going to take into consideration all of the different nuances associated with the boundary conditions along the azimuthal angles. So, big theta as a function of theta is equal to A times P sub L, or P m sub L, smaller l, cosine of theta, where L equals 0, 1, 2 to n minus 1. Now PL with m sub L up in the numerator as a function of cosine theta is called a Alessandra polynomial. If you go to table 8.3 in Atkins, you'll see a list of different functions exactly like you saw with the Hermite polynomials, where L and m sub L are going to be 0, 1, 0, 2, 0, or 1, 1, and there's just going to be a function. They're not as scary as you think, so just go look at table 8.3 and you will find those. Okay, so that's big theta. Big phi is equal to A e raised to the I m sub L theta, phi, where m sub L is equal to minus L to 0 all the way to plus L. Okay, if you combine these two together, so this is actually a very special term. It's called the spherical harmonic of theta and phi. And if you solve the Schrodinger equation, get the energy states by operating on this wave function by the Hamiltonian, you get the energy L times L plus 1 h bar squared over 2I. And then I think I have I written, there might be a mistake in there, L equals 0, 1, and 2. And so you'll have your energy states, and I believe I is going to be your moment of inertia. Again, check Atkins out. And if you take the spherical harmonic and you plot the spherical harmonic squared, what you're going to get for L equals 0, L equals 1, and L equals 2, you might get some very, what's the word I'm looking for? Familiar shapes that look something like this. So, timer's done. So, you can see that by plotting, good God, stop it. By plotting the spherical harmonic, which is the angular components of a particle bound to a sphere, the angular momentum quantum number is L. If you plot those of the square of the wave function, which is your probability distribution, that's where you get your orbitals. Okay, I'm done.